I welcome you all to the Spark Research YouTube channel. This is Dr. Veer Chandra, Assistant Professor in the Department of ECE. Here is the another session for this course signal processing. And in this session, we are going to talk about this analysis and for discrete time system, signal and system. So this is the part first of unit first. And in this session, primarily, we are going to talk about the FIR filter, that is finite impulse response filter, and we'll also see the frequency response of this FIR filter, including this odd symmetry and even symmetry. So here is the syllabus for this unit 4, and in this session we are going to talk about the how we'll design the linear filter and the frequency response of your FIR filter or an even symmetry, right? And apart from that, the major important topic is your window technique, right, in this unit. So we will talk about this window technique in the next session. So question number first is, what is this FIR filter? So FIR nothing, this is your finite impulse response. Why finite impulse response is important? See, first thing is that whenever we are talking about this filter, we want to pass the some particular band that is based on the type of the filter. But question is that how will you do that, right? So the thing is that, like, if you are considering this graph, that is this belongs to the low pass filter, so low signal is passing here. But problem is that how will you design your hardware? That is the challenge. So in order to design the hardware, like, it must, like, in the digital format, if you wanted to design, then you need the finite impulse response, right? So that all the impulse response can be added to design your finite impulse response filter, right? So FIR filter. So in order to do so, we are going to combine the multiple impulse response, and then we will finally have the FIR filter. So this is the technique, right? So in order to do so, we are going to use this impulse response, and also we'll see how can we design the FIR filter using the window technique, right? Okay, so what is the advantage of your FIR filter? First, relatively easy to design, of course, and more efficient, computationally more efficient. Means what? The since this is finite one, so computation is very easy and it will be efficient. If, like, suppose if more numbers are there in between two frequency, and then of course the computational will be very high, and since we are considering the finite number, so it will be very easy to the get design the filter, right? So FIR filters are implemented in hardware or software. So implementation of your FIR is very easy because of the number of the impulse response is fixed, finite. The phase response is linear also, this is another advantage, and properly implies the phase is a linear function of the frequency. FIR output is delayed by the sum amount of all time frequencies, right, in order to phase distortion, right? FIR filters are always stable also, and for a finite input, your output will be finite, so stability also matters. And along with that, some disadvantage, they require more memory and the calculations to achieve the finite response. Okay, so now how exactly, now question is that how will design? So finite impulse response filter format. So first thing is that an FIR filter is completely specified by the input output relationship by this equation. And what is this equation? So yn, this is your output, and summation of I equal to 0 to k is any number, and the x of n minus a, so this is your input, right? And what is this bi? Bi is nothing, your FIR filter coefficient, right? And also you can rewrite this equation like b naught xn plus b1 xn minus 1 plus b2 xn minus 2, and so these things then will depends on the total number of the responses that you required. Finally, if you will take the z transform of this yn, then you will get the yz is equal to b naught xz and b1 z inverse xz, right? Why is it so? Because we are shifting the delaying in the time domain. So n minus 1 means just multiply by z to the power minus 1. If n minus 2, then z to the power minus 2. N minus 3 means z to the power minus 3 and xz will be there, right? So further you will get the x, the hz, yz divided by xz, that is equal to h of z, that is the filter. Okay, so one question let's take here. So in this question it is asked yn is given, the output is given here, that is 0.1 xn. So this one is given and you have to find out the transfer function, filter length and impulse response, three things. So first find out the transfer function. So in order to do so, yz is already given here, right? And so like yn is given, so like just convert into the z transform, you will get this yz and then take the common xz and then get the h of z, that is yz divided by xz, right? So this is the final answer of your transfer function. Now length, so filter length is nothing, that is k plus 1, so here it is 3 and this part is nothing, this is b0 and 0.25, that is your b1 belongs to the z minus 1, that is y, right? And this is your b of 2. So you get all the values and then take the inverse transform of the transfer function of this z, h of z, you will get h of n, right? So that will be equal to this function. Clear? Okay, so now Fourier transform design. So here, ideal low pass filter with a normalized cutoff frequency whose magnitude frequency response in terms of the normalized frequency. So actually, what is our target? Now our target is to take the Fourier transform of the filter. So how we'll do that? Okay, actually, major thing is that like here see we have the one rectangular function, but if you are going to design your the FIR filter, we have to combine multiple rectangular type of function. Why? Because you are going to add the multiple impulse responses. So here suppose we are adding one impulse response which have the frequency range of minus omega c to plus omega c, right? And then next one will be twice pi plus minus omega c, and the left one twice pi plus minus omega c. Similarly, next one like will have the 4 pi and plus minus omega c, right? Similarly, left side will have minus of 4 pi and plus minus omega c. Similarly, we can keep on adding, and the rectangular function will depends on the number of the terms that we are using, right? So finally, we can get the value of h of n. So h of ez will be equal to 1. 1, this is only in between, the in between 0 to omega c, right? So that in that case, it will be 1. And in this gap, right? In this gap, so this is the gap. So in this gap, of course, your h of ez equal to 0. So nothing is there, no rectangular function. So in this gap and in this gap, so in this all these gaps, it will be 0. So if your omega is in between omega c to pi and not pi, pi to pi to 3 pi like that, in that case it will be 0. So here we are considering 3 only. So this case is okay, right? So here now further you can write h of n is equal to 1 by twice pi, right? From here only, and that is minus pi to pi and h of e to the power j omega and e to the power minus j omega, and so inverse Fourier transform, right? Further here c pi, here the constant you can write like this. Okay, so now so now we are actually going to find out the final the value of your characteristic function, right, for your FIR filter. So in order to do so, here if you will see, this is the impulse response of an ideal digital low pass filter. Here suppose now h of n like 1 is here, one impulse response, along with that the neighboring impulse responses are there. So it is very clearly showing because low frequency is passing now, so it is belongs to the low pass filter only. So how we'll find out, how we'll characterize this? So here hz is nothing, h of n z to the power minus n, and here like total number of the impulses you can write like this. Okay, and h of n is equal to nothing, h of, you just take the inverse function of your h of z, h of z. Why this h of z? Because you have these impulse responses in the z function, like in the frequency domain, right? Now h of n, you can get it 1 by twice by an inverse function, right? Inverse z transform. So you will get h of n. Now if you will check n is equal to, just put the value of n is equal to 0 in this equation, in this particular equation, then what will be the value of h of n? Put here at this part will be 0, so e to the power 0 is equal to 1. So integration minus pi to pi, you will get omega c by pi. This is only for what? This one, right? So h of 0, right? For remaining parts you have to calculate. So if n is not equal to 0, again put solve this equation, you will get the sinc function. Why is it so? Already we know that the transfer function of the rectangular function is nothing, that is your sinc function, right? So finally you can conclude this is at 0 and this is at the, now if n is not equal to 0. So you can conclude for low pass filter hn is equal to omega c divided by pi for n equal to 0, and sinc function if n not equal to 0, just now we saw. And so what is this low pass filter? Low pass filter is nothing here, if only low frequency is passing, that is low pass filter. And if here see omega f low high frequency, like suppose more than 100 frequency, whatever 100 hertz, all frequency is passing, like amplitude is 1. So this is belongs to the high pass filter, and in this region will not pass, this region will pass, and this region will pass. So this is band stop type of filter. And here like this band will pass in between omega 1 to omega 2 and omega 3 to omega 4, right? So this is the band pass type of the filter. Okay, so for all these type of the filters you can find the impulse response, right? So we have the derived for the low pass filter. Similarly you can find. Now here if you will see the, for n is equal to 0, what will be the value of hn? So denominator always it is the pi only, and the numerator if you will check, then this is nothing, the passband frequency only, right? And for n not equal to 0, already this is nothing, your sinc function. So in this way you can remember. Okay, so the same things you can also rewrite, like if this is your output for your low pass filter only, and h of n is nothing bn for if m, the n is less than in between 0 to m minus 1. M is the total number of the impulse responses, right? And yn is in terms of the b naught you can write. So already we have seen. So yn is nothing, this is h of k, that is your transfer function, and x of n minus k, that is your input. So in this way you can find out the output, right? Now actually these FIRs may be of two types. One is your symmetric and one is your anti-symmetric, right? So what are these? So we'll see now only. So major thing is that we want to reduce the computational, right? The number of computations. So we want to make it more faster and efficient, so that is why we are moving towards the symmetric. Like if symmetric is there, we can no need to do the computation same things by twice, so we can take it half, right? So hz will be h of n, hz and hz to the power minus n. So how we'll do, let's see. So this is the case, first case is a symmetry. So here see how many responses are there. Response number 1, response number 2, response number here the 3, and here response is your 4, and this is your 5, this is your 6, and here is your 7, here is your 8, right? And here is your 9 response. Total 9 impulse responses are here. And center is of course the fifth one. So here the fourth one, here this is your center. Along with that, now if you will see, this is the symmetric. Why? See, this sixth one and fourth one both have the same amplitude. Seventh one and third one both have the same amplitude. Similarly, eighth and second have the same amplitude. Ninth and first have the same amplitude. These both are same, right? And these both are same means you can keep one mirror here and both are mirror image. So this is called the symmetric. So if you'll compute the right one and then make it double, you can get the final FIR, right, for both left and right, entire one. So this is the concept. Similarly, this is the center, the symmetry from the center. And so here the odd numbers are there, means total n is equal to m is equal to how much? Here m is 9. So this is why called odd symmetry. In this case, now see here m is equal to 8, right? So this is called the even symmetry. So in this case, we cannot take at the the particular value. Here we have to take the the at the mid. So mirror we can keep at the mid one only. So right side you can see 4 impulse response, left side also 4 impulse response. So that is why this is called even symmetry. This is the just examples of the anti-symmetry. So here you can keep your mirror here or randomly anywhere. So of course this is the example of the the non-symmetric or anti-symmetric. So let's see how to solve. So suppose symmetric for m is equal to odd. So total number is how much? 9. M is equal to 9 here. So now let's find out the transfer function, right? So h of z first, h of z will be n is equal to 0 to m minus 1 total h of n and z to the power minus 1. This is the basic equation, right? And from here only we are going to solve this. So h of m minus 1, m is how much? 9. So 9 minus 1 divided by 2 means 4. So why is this 4? This is at the mid. So first we are going to find out for mid h of z and then remaining. Remaining we'll find out like here n minus 9 minus 3 divided by 2. So we'll get this one, this and the remaining. And then simply make it double, right? So then solve this and you will get the actually the cosine functions here, just e to the power theta and e to the power minus theta you will get here. So if you will add in this, you will get the cosine function, right? Further, if you will solve, then you will get the h of w, that is transfer function. And here this is the double. Why is this double? Because left and right, right? And this one belongs to the center one, right? So left and right. Now no need to calculate separately, you can directly make it twice. So h of w, that is transfer function, is nothing minus of omega m minus 1 divided by 2 if h of omega is less than 0, right? And this is again plus pi if omega is less than 0. So this is the final equation that you can remember. Similarly, for if m is equal to even, means we have got the values for transfer function for odd. Now similarly for even, how will you find out? So here in this case, we are going to put our mirror here in between. So now the right side will have the numbers and the left side also we have the some impulse response, but at the center we do not have anything, right? So first term, there is no first term, no need to it, only we will keep this term, right? Already we got these values, so the same value you can copy paste here. So minus omega m minus 1 divided by 2 for greater than 0 and m minus 1 divided by 2 plus pi for less than 0. Okay, thank you to join the session. If you have any doubts, please drop a comment.